With the most advanced spacecraft in human history, we are going farther than we have ever gone before. It looks like the absolute triumph of technology. But there is a paradox. The greatest danger is not a complex rocket failure. It is the moon itself, and it has zero respect for our technology. Even our most durable spacesuits are shredded within hours by lunar dust, which acts like microscopic shards of glass. Our most advanced shields cannot stop us from absorbing 450 times more radiation every day than we do on Earth. And our smartest engineers cannot stop a 300-degree temperature swing from creating metal fatigue. But the real paradox is this. On this multi-billion-dollar mission, we have no idea what the human body will do in 1/6 gravity for more than 3 days. If this chasm between technological hubris and brutal reality excites you, subscribe to the channel, because you are about to see why staying on the moon might just be impossible. Let's begin. For years, we thought the moon was a passive museum of geology, a giant, chargy ancient rock, inert and static. We believed that because it was conquered once, it could be conquered again. Because the Apollo astronauts walked there and came home. So we took that as proof that humans could handle it, and in the narrowest technical sense, that was true. But the science accumulated over the last half-century has revealed just how incomplete that comforting picture was. The moon, it turned out, is not passive geology, and we now know that the silence of the moon is not a sign of surrender. It is merely evidence of a much more patient hostility. To understand the first layer of this hostility, you have to accept that the thing beneath your feet is not soil, it's regolith. But that scientific term conceals just how alien the reality is. Imagine a world bombarded continuously for 4.5 billion years, with no erosional processes to soften what is created. So, what you get is not sand, it is glass, shattered at a microscopic level. Because on Earth, rock is rounded over millions of years by water and wind. Rivers tumble it, rain dissolves it. But on the moon, none of that exists. So, the particles there, under a microscope, look less like soil and more like tiny, sharp-edged hearts, chemically active knives. These particles are small enough to bypass the natural filtering systems of the nose and upper respiratory tract. They can penetrate directly into the deepest parts of the lungs. And after the Apollo missions, visible abrasive damage was found on the astronauts' suits after just a few hours of surface activity. This was the first proof that the moon's surface wasn't just empty. It was a sign that it was actively attacking you and your equipment. But threatening lungs and machines is not the only thing this dust does. This is only the beginning of the story, because there is another danger waiting for you on the moon. And this one, you cannot even see. Right now, Earth's magnetic field protects our planet from a constant bombardment of particles. It is an invisible shield we don't notice, because we have never lived without it. But the moon has no such shield. It has an extremely weak and patchy magnetic field that does nothing on a global scale. So every high-energy cosmic ray from across the galaxy, every charged ion erupting from the sun, strikes the surface at full, unmitigated velocity. The numbers at hearts measured by China's Chang'e 4 mission make the situation clear. The radiation dose on the lunar surface is about 1,369 microsieverts per day. Let's put that in context. An average person on Earth receives only about 3 microsieverts per day. This means that standing on the moon on a normal, quiet day means absorbing roughly 200 times more radiation than you would on Earth. But that number is even about twice the dose received by astronauts on the International Space Station. But that's just the baseline. When the Sun decides to create a particle event, which happens with little reliable warning, those numbers can spike to lethal levels within a single hour. And while this invisible bombardment continues, the moon wears you down with a completely different method. This is the thermal cycle. The lack of an atmosphere on the moon means there is nothing to moderate the temperature. So, at lunar noon, the surface temperature reaches positive 127 degrees Celsius. That is above the boiling point of water. Just 14 Earth days later, as the lunar night begins, that same surface cools to minus 173 degrees Celsius. That is a full 300-degree temperature swing, a range that most materials on Earth will never encounter in their entire lifetime. Consider the effect of this cycle on every single piece of equipment, every bolt, every seal, every wire. Materials expand when they heat up and contract when they cool. So, different materials at every joint change size at different rates. This creates a slow, methodical mechanical fatigue. Apollo hardware was built to last for days. But the engineering requirements for a habitat that must last for years are completely different, because in the permanently shadowed craters of the polar regions, the temperatures drop even lower, approaching minus 250 degrees Celsius. That is colder than Pluto. The moon doesn't break equipment suddenly like a sandstorm. It breaks it slowly, with every single cycle of day and night. So what you have are microscopic shards of glass, a constant bombardment of radiation, and a 300-degree temperature cycle that fatigues everything. But none of these dangers exist in isolation. They interact, they amplify each other, and they combine into a single survival problem that humanity has never had to solve for more than a few days. So when you land on the surface of the moon, you don't just encounter an absence of comfort. You step into the presence of an active, shock-unified hostility, and the most insidious, most unexpected weapon of this hostility was the very most insidious, most unexpected weapon of this hostility was the very ground beneath their feet. Because when the Apollo astronauts placed seismometers there, nobody expected the instruments to be very busy. The moon was assumed to be geologically dead, a cold, jagged solid rock, a world that had finished doing anything interesting billions of years ago. The expectation, therefore, was silence, but the data that came back from the seismometers completely shattered that assumption. Because the moon is not geologically dead, it is geologically active, in a way that produces constant seismic activity. During the operational lifetime of the Apollo seismic network, from roughly 1972 to 1977, the instruments recorded over 13,000 seismic events. 13,000. But the nature of these events is far more alarming than earthquakes on Earth, because on Earth, seismic waves are absorbed by the planet's relatively soft, partially molten, and water-saturated rock, and they dampen out within minutes. The ground shakes, ceases, and then it stops. When on the moon, it's different. Its solid, cold, and dry crust does not absorb seismic energy the way Earth's does, so the waves travel through it, bouncing, echoing, and resonating. The scientists who studied the Apollo data described it as the moon ringing like a bell. A moonquake doesn't last for just a few seconds and then stop. It can last for minutes, sometimes for over an hour. This creates a stress profile that is completely different from the 30-second jolt that terrestrial earthquake engineering deals with. It is a continuous, low-level vibration. And that vibration, it is not a trivial detail for any structure that will be built on the moon, because it completely changes the fatigue, loads, and failure modes in materials. You are no longer building on a solid foundation, so you are trying to erect a structure on top of an instrument that is constantly ringing. But this movement beneath the surface is only half the threat, because the lack of atmosphere also leaves the moon defenseless against a constant assault from above. This assault, is the micrometeorite bombardment. These particles, ranging from grains of sand to small pebbles, strike the surface at an average speed of 20 kilometers per second. That is about 72,000 kilometers per hour. The speed of a rifle bullet is only 1 kilometer per second. So, a micrometeorite coming in at 20 kilometers per second carries the kinetic energy of an object going 20 times faster than a bullet, a particle of just 1 milligram. The weight of a small ant possesses enough kinetic energy to pit metal surfaces, shatter glass, and penetrate materials that would stop a conventional bullet. On Earth, almost none of these particles reach the surface. They burn up and vaporize in our atmosphere. But the moon has no such protection. This bombardment is constant, a slow, patient, and cumulative kind of destruction. Solar panels develop pits that reduce their efficiency. Windows and visors develop microfractures that scatter light. The moon slowly wears things down, but it does so in a way that bears no resemblance to erosion. So, the legacy that Apollo left us was not just a story of triumph, it was also a warning. Their experiences on the lunar surface changed how engineers thought about long-term missions. They discovered that the dust would not be a one-time contamination event. It would be a system, a cycle, and every astronaut who went out and came back would add another layer to that cycle. The lunar hay fever symptoms experienced by geologist Harrison Schmitt on Apollo 17 were the first indication of just how biologically reactive this dust could be. Sneezing, eye irritation, sore throat, all of it emerged after exposure to the dust that had infiltrated the cabin. But Schmidt's exposure lasted for hours, not weeks, so Apollo gave us a warning sign. But it did not give us enough information to know just how serious that warning was, because we never tested what long-term exposure meant. And this is the reality that Artemis now faces. We have a sharp, abrasive dust, a constant and sometimes suddenly lethal radiation environment, extreme temperature swings that fatigue materials, a ground that rings for minutes or even hours, and an invisible rain of bullets falling at 20 kilometers per second. None of these dangers, on their own, might be a mission ender. But they all operate at the same time, constantly, as a unified system of pressure. The moon does not attack you violently. It wears you down patiently. All of these theoretical dangers exist in engineering models and risk analyses. But beyond the cold numbers and warnings, the real question is this: what does it actually feel like to live in this environment? The Apollo astronauts were the first-hand witnesses to this hostility. How did their findings, holds, bring this theoretical picture to life? Because Apollo didn't just prove we could go to the moon. It also gave us the first clues as to just how dangerous it was. And those clues did not come from theoretical models, or laboratory simulations. They came from the shocking, first-hand testimonies, from the mouths of the first humans to go to the moon. Because when the Apollo logs were opened, the truth behind the moon's silence was far more disturbing than anyone had predicted. And now, here are those findings. The first shock, is biological. Harrison Schmitt, the geologist on Apollo 17, should not have gotten hay fever on the moon. It was impossible. The moon was an airless, sterile world. There was no pollen to trigger an allergic reaction, no microorganisms, nothing. But the symptoms were there. They were real. Schmitt began sneezing almost immediately after returning to the lunar module. His eyes watered. His throat became irritated. This was after a 3-day surface mission. It was no coincidence that Schmitt was the Apollo astronaut who spent the most time on the lunar surface, because as the exposure increased, so did the body's reaction. This showed scientists a terrifying truth. The problem wasn't something on the moon. The problem is how it was the moon itself. At that grey dust, that seemingly harmless regolith was not biologically inert. It was active. The body was perceiving it as a foreign invader. Because those particles, having been bombarded by space radiation for billions of years, had become chemically reactive. And now, when they entered a human respiratory system, the immune system sounded the alarm. This was the first biological proof that the moon wasn't just a piece of rock. It was an environment that was at war with its own surface material. But the dust wasn't just targeting biology. It was also defeating one of humanity's greatest technological achievements, the Apollo spacesuit. These suits were engineering marvels. They had pressure seals that had to work perfectly. They had bearings that had to allow for flexible movement. But the dust didn't care. After just a few hours of surface activity, the astronauts reported that the suit joints moved differently. Zippers and closure mechanisms felt gritty, in a way that was impossible to fully clean. The photographs revealed the truth. Spacesuits that had turned grey in a matter of hours. This wasn't just contamination, this was an assault. The microscopic glass-like particles of dust were cutting the fibers of the fabric, abrating the seals, and getting in between moving parts. This shouldn't have happened. A system designed with millions of dollars and thousands of hours of engineering was not expected to be degraded so quickly and so effectively by simple dust. Because this showed that the moon's defense mechanism was not just passive. The moon was using an active, abrasive force against everything you brought with you. And the most terrifying part was that this infiltration was unavoidable. There were procedures designed to minimize contamination, but it was impossible to eliminate it. After every single excursion, that sharp, reactive dust was entering the astronauts' living space, and it was staying there. And then the ground moved. But not like it does on Earth. When the Apollo seismic network recorded over 13,000 seismic events between 1972 and 1977. That was the first shock, because a world considered geologically dead, was not supposed to be this active. But the real shock was the nature of these tremors. When the Apollo scientists listened to the data, What they heard was not an earthquake. It was the ringing of a bell. On Earth, an earthquake happens, and the seismic waves die down in a few seconds, maybe a few minutes, because our planet's internal structure absorbs the energy. But the moon's interior is dry, cold, and rigid, so it does not absorb the energy. It reflects it. This meant that a single tremor could last for minutes, and in some cases, for over an hour. An earthquake would happen, and the ground would just keep vibrating, fading, but not stopping. This was not physically expected. It showed that the moon's fundamental structure, instead of dissipating stress, was trapping it and amplifying it. This meant that any structure placed on the lunar surface would be subjected to a type of stress completely alien to our engineering intuition. A constant vibration. The dust infiltrated our bodies. It tore at our suits. The ground rang like a bell beneath us. All of this was observed during missions that lasted only a few days. This puts the Artemis program into a completely different context. The question is no longer, can we go to the moon? The question has become, can we stay there? Because Apollo's brief visits proved that this hostility was only the beginning. And the question of what happens in the long term is keeping not just engineers, but biologists awake at night. Because what we know about what the moon will do to the human body is a drop in the ocean compared to what we don't know, especially when it comes to that most fundamental, most invisible threat, radiation. Because the numbers coming from the surface of the moon are not just worrying. They are radical enough to shake our most basic assumptions about long-term human presence. And these numbers, Lach, came long after Apollo. China's Chang'e 4 mission landed a radiation dosimeter on the far side of the moon, and what it measured changed the entire equation. The number was 1,369 microsieverts per day. That number might not mean much on its own. But when you compare it, a shocking picture emerges. The average human on the surface of the Earth receives about 3 microsieverts of background radiation per day. This means that spending just one day on the moon is to be exposed to a radiation dose equivalent to almost a year on Earth, roughly 200 times more. This was about twice the dose that even astronauts on the International Space Station are exposed to, and they are still within the protective embrace of Earth's magnetosphere. On the moon, that embrace is gone. There is no protection. So when this data came in, Achasta said, the scientific community was in a state of quiet shock, because this proved that the dream of establishing a long-term base on the moon was far more than a simple engineering problem. It was a biology problem. It was a fundamental question about how long the human body could survive in an environment it did not evolve to tolerate. Because these numbers were for a normal day, when the sun was at its calmest. But the sun is not always calm, and this was proven in August of 1972, in the month between the return of Apollo 16 to Earth and the launch of Apollo 17. The sun produced one of the most intense solar particle events ever recorded. It was a storm, a sudden or violent release of high-energy protons. If there had been astronauts on the lunar surface during that storm, the result would have likely been fatal. This shouldn't have happened. The probability of an event this violent, being squeezed between 2 manned missions, was astronomically low. But it happened. The radiation dose it delivered during its most intense phase was estimated to be at levels that would cause acute radiation syndrome within hours and exceed survival thresholds without adequate protection. The analysis after the event horrified scientists and engineers because it showed just how critical a role luck had played. Mission planners do not rely on luck. But this event proved that there was a risk they could not completely engineer away. Space weather forecasting has improved since then, but the time between the detection of a particle front and its arrival at the Moon is still measured in minutes, or at best, hours. 1 hour. That might be all the time an astronaut on an excursion has to get back. And that meant that every single mission outside on the Moon had become a cosmic gamble that no one could fully predict. And just in the very place seen as most promising for long-term settlement, the Moon delivered one final blow. The south pole of the Moon. This is where the water ice is, the one resource required for a permanent presence. This is the primary target for the Artemis program. But a study published in 2024 cast a shadow over this hope. When researchers studied the geology of the region, they found evidence of active fault lines, but these were not ancient fractures that had been dormant for millions of years. These were structures that showed signs of recent movement. This seemed impossible, because the permanently shadowed craters, the very places where the ice is found, were supposed to be the coldest, most stable, and most dead regions of the Moon. But this study suggested the opposite. As the Moon's interior cools, it shrinks, and this shrinkage creates stress in the crust. This stress was being released along fault lines, and some of these fault lines were directly under or very close to planned Artemis landing sites. This meant that the very resource we needed most to survive was located on what might be the most unstable ground. So when the picture is complete, what emerges is not a land of adventure, but a survival nightmare, a biologically reactive dust, a radiation field 200 times more intense, solar storms that can become lethal in an hour, 300-degree temperature swings that fatigue materials with every cycle, a ground that rings like a bell, and active fault lines where the most valuable resource is found. Apollo didn't just give us a warning. It told us that the Moon is not just a place to visit. It is an environment designed at every level, with every available mechanism of physics, chemistry, and biology to destroy you. But how exactly do all of these dangers, these mechanisms, work? What is it about the chemistry of the dust that makes it so dangerous? What are the biological effects of the radiation? What exactly does that 300-degree swing do to the seals on a habitat? Because to understand the hostility of the Moon, you have to understand not just what it does, but how it does it. Because behind this hostility, there is no random chaos. There are, instead, extremely methodical, predictable, and merciless physical and chemical processes. Now, we slow down. We move away from the fast-paced shocks and look under the hood of this hostility. We will examine, one by one, the mechanisms the Moon uses to destroy you and your technology, because the danger is hidden in the details. And the first detail, what, is that dust beneath your feet. To understand it, imagine taking a piece of glass and smashing it on a concrete floor. Now, imagine doing that for 4.5 billion years. In a place with no air and no water. An environment with no process to round the resulting fragments. That is the regolith on the lunar surface. It is the result of a process scientifically known as impact gardening. On Earth, rocks are turned into soil by weathering, like water freezing and expanding, wind abrading, and rivers tumbling. But on the Moon, none of these processes exist. The surface is only impacted, and what those impacts produce remains as sharp and as reactive as the moment it was created. This is why lunar dust is rich in silicate minerals. This is the same family of minerals that causes the disease silicosis in coal miners and sandblasters on Earth. But the lunar version is far more insidious. Because these silicate particles, bahants, are small enough to bypass the natural filtering mechanisms of the human nose and upper respiratory tract, they can penetrate directly to the alveolar region of the lungs, where gas exchange occurs and where the immune system is least equipped to deal with foreign matter. This doesn't just make lunar dust a mechanical irritant, it turns it into a potential biological weapon. Because unlike its terrestrial counterparts, the chemistry of this dust has never been neutralized by reacting with water and air. It has been waiting, frozen in a chemically ready state for billions of years. So, it is not just abrasive, it is dangerously reactive. But key, the danger of the dust isn't limited to its shape and basic chemistry. There is another layer. It's a process known as space weathering. Think of every single dust particle on the lunar surface being exposed to a constant bombardment of solar wind and cosmic rays for billions of years. This process alters the outermost atomic layers of the particles. Just like a balloon rubbed against a wall becomes electrostatically charged, lunar dust becomes electrostatically charged by the sun's ultraviolet radiation. This means it doesn't just sit passively on surfaces, it actively clings to everything it touches. Spacesuits, gloves, helmet visors. The surface of a glove that touches the lunar ground doesn't just have dust on it, it has dust bonded to it by electrostatic attraction. So, when this dust is brought into a habitat, it doesn't stay put. It gets resuspended in the air. It migrates. It gets everywhere. But the problem of chemical reactivity goes even deeper. Space weathering creates what are called dangling bonds on the surface of these particles. These are atoms that are chemically unsatisfied, hungry to grab an electron. When these particles encounter biological tissue, this electron hunger translates into oxidative damage at the cellular level. Soil on Earth is not this reactive. Because water and air have satisfied these dangling bonds billions of years ago. But lunar dust is chemically pristine and ravenous. So, the hay fever that the Apollo astronauts experienced was not a simple allergic reaction. It was an inflammatory response of their bodies to a chemical assault they had never encountered before. The dust wasn't just sharp, it was chemically aggressive. Now, let's move from this microscopic danger to a threat on the macro scale. The 300-degree thermal cycle. To understand this mechanism, imagine taking a paperclip and bending it back and forth, over and over. At first, nothing happens, but every cycle creates microscopic damage in the metal structure. And after enough cycles, the paperclip breaks. That is exactly what the moon does to your equipment. At lunar noon, the surface temperature reaches positive 127 degrees Celsius. 14 Earth days later, as the lunar night begins, that same surface drops to minus 173 degrees Celsius. That is a full 300-degree temperature swing. Consider any engineering structure is made of different materials. A bolt a seal, a wire. Every material has its own unique coefficient of thermal expansion. This determines how much they expand when they heat up and how much they contract when they cool. Also, over a 300-degree cycle, a bolt expands and contracts at a different rate than a seal. In one cycle, this effect is manageable. But over 10 cycles, 100 cycles, 1,000 cycles, this is cumulative mechanical fatigue. Gaps form in seals that were initially airtight. Joints that moved smoothly begin to stick or develop play. Thermal stress cracks propagate in structural elements. The Apollo hardware, Hostility, was built to withstand only a few days, only a handful of thermal cycles. But a permanent base for Artemis, Hypervelocity, must maintain its pressure integrity, its thermal insulation, and its mechanical function for years, for hundreds of cycles. And this hardware cannot be fully tested on Earth, because there is no 300-degree thermal cycle on Earth. The first real test of the equipment will happen on the Moon, the very place it is designed to survive. The Moon breaks equipment slowly, methodically, and with every single cycle of day and night. So what we have is a dust that is physically sharp, chemically aggressive, and electrostatically sticky, and a relentless thermal cycle that slowly but surely weakens all materials. These two are the Moon's most fundamental surface weapons, and both are a direct result of the lack of an atmosphere. One from the lack of weathering, the other from the lack of a thermal buffer. But these are just the threats on the surface and in the temperature. Among the Moon's deadliest weapons are those that are completely invisible, the forces that move through that silent vacuum and shake the very ground beneath you, because the Moon's radiation field and its seismic activity are not simple dangers. They are systems with complex multi-layered mechanisms of their own. And understanding how they work, and understanding how these systems work, is vital to grasping the true nature of the Moon. Because these invisible threats are just as physical as dust or temperature, they just operate by different rules. And the first of these rules is the most fundamental weapon the Moon uses against you: the absence of an atmosphere. This is the key to how the radiation field becomes so dangerous. On Earth, the magnetic field and atmosphere around our planet act as a multi-layered shield. It deflects most of the charged particles from the Sun, and it absorbs the cosmic rays from deep space. But the Moon has no such luxury. So the Moon is completely exposed to two main types of radiation. The first is known as galactic cosmic rays. You can think of these as high-energy atomic nuclei, accelerated to near the speed of light by events like supernova explosions elsewhere in the galaxy. As they pass through biological tissue, they cause ionization along their path. That is, they knock electrons off of atoms. This can break chemical bonds, including the bonds in DNA. The body's repair mechanisms fix most of the damage. But that repair process is not perfect. Over thousands and thousands of exposures, the error rate accumulates, and that increases the long-term risk of cancer. Galactic cosmic rays are like a constant background noise coming from all directions. You cannot escape them. But the second type of radiation is far more violent: solar particle events. These are sudden, intense bursts of high-energy protons, associated with solar flares and coronal mass ejections. If galactic cosmic rays are like a constant drizzle, solar particle events are like a sudden hurricane. During a major event, like the one in August 1972, the radiation dose can spike to levels that can cause acute radiation sickness within hours. This is an immediate, and urgent threat to life. The only defense against these storms, is to get behind a shield. Usually, a thick layer of regolith or a specially designed storm shelter. But there's a problem here. Shielding against galactic cosmic rays is not as simple as just adding more mass. Because when these high-energy particles interact with the shielding material, they can create secondary particles. This means, your shield itself can become a source of radiation. This means that beyond a certain thickness, adding more shielding can actually increase the exposure rather than decreasing it. This is an engineering paradox that makes solving the radiation problem on the Moon incredibly difficult. So, the radiation problem on the Moon is never fully solved. It is only managed, and that management is always imperfect. Now, let's move from the invisible threat above to the hidden threat below. Moonquakes. The data from the Apollo seismometers revealed that the Moon was not just active, but it was being activated by multiple mechanisms. The most common of these are called deep moonquakes. These occur deep within the Moon's interior, about 700 to 1,200 kilometers below the surface. They are triggered by the tidal stress of the Earth and Sun on the Moon. Imagine the Moon not as a solid sphere, but as an object that is constantly being slightly squeezed and released as it orbits. This causes stress to build up in the Moon's interior and be released as small seismic events at regular intervals. While these are generally low in magnitude, they create the background seismic hum of the Moon. But more concerning are the shallow moonquakes. These occur within the upper few hundred kilometers of the crust, and their cause is not fully understood. They are likely related to the Moon cooling and contracting over geological time. Some of these events have reached a magnitude of about 5 on the Richter scale. On Earth, that is enough to cause significant damage. But on the Moon, the result is much more disturbing, because the Moon's dry and rigid crust does not efficiently absorb seismic waves, so the energy reverberates inside, causing the Moon to ring like a bell. A single tremor can last for minutes. This means a structure is subjected to a prolonged low-frequency vibration. This is a completely different type of stress from the short, sharp jolts that engineers on Earth design for. This means that structural fatigue and resonance-induced damage become a much greater concern. These large-scale geological and radiation threats are the Moon's most obvious hostilities. But the most insidious weapon in the Moon's arsenal is perhaps its smallest, micrometeorites. These are sand grain-sized particles, striking the Moon at an average speed of 20 kilometers per second. This speed is about 20 times the speed of a rifle bullet. Since kinetic energy increases with the square of the velocity, these tiny particles pack a disproportionately large punch. A particle of just 1 milligram can pit metal surfaces, shatter glass, and penetrate the outer layers of a spacesuit. On Earth, our atmosphere protects us from this constant bombardment. They burn up before they reach the surface. But on the Moon, there is no protection. This means that any structure on the lunar surface is subjected to a constant sandblasting process over time. Solar panels slowly lose their efficiency. Optical surfaces get scratched. Seals and gaskets get eroded. The probability of a single large impact may be low. But the cumulative effect of millions of tiny impacts is an inevitable degradation over time. This is another of the Moon's patient methods of attack. Not an instant catastrophe, but a slow and methodical erosion. So what we have is a radiation field that shreds D, N, you're an A ground that rings like a bell, and an invisible sandstorm raining down at supersonic speeds. All of this is added on top of the dust and the temperature cycles. Each of these mechanisms might seem manageable on its own. But the real power of the Moon is that it uses them all at once, relentlessly and in combination. This is a survival problem. But so far, we have only talked about machines and physics. Beyond all these engineering and environmental problems, there is a system that is far more complex, far more fragile, and far less understood. The human body. Because when the Artemis mission launches, we will not just be testing new technologies. We will be testing the limits of human endurance in a domain we have never entered before, and the results of that test could determine everything about our future on the Moon. Because the most terrifying part of what the Moon does to us, because the most terrifying part of what the Moon does to us is that we do not know how our bodies will respond. And now, we come to the climax of the video. We are shifting gears because everything we've talked about so far has been about machines, the ground, the environment. But the real unknown, the real fear, and the real adventure is in human biology itself. And the first discovery in this field, yes, was a revolution. A data gap that simply did not exist in the scientific literature. When impossible. But it was real. And now, we enter that gap. The first epic moment. The 1/6 gravity blind spot. This shouldn't exist. We do not know what the human body will do when exposed to 1/6 gravity for months, or even years. This is not a small detail. This is the giant black hole at the center of whether we can live on the Moon or not. Because all of our plans, all of our habitat designs, all of our mission durations are based on the assumption that the human body will endure this environment. And that assumption is based on incomplete evidence. We have decades of data on microgravity from space stations. There, the body begins to change immediately. The bones, especially weight-bearing ones like the spine, hips, and legs, begin to lose their density. The rate is not subtle, between 1 and 2% per month. This means an astronaut can lose a significant fraction of their bone mass in 6 months. In a year, the loss becomes clinically significant. This is similar to the progression of osteoporosis. But it is compressed into a much shorter time frame. So, we know that in microgravity, the body begins to destroy itself. But the Moon is not microgravity. It has about 1/6 of Earth's gravity. This means there is some mechanical loading on the bones and muscles. There is something for the cardiovascular system to work against. But the question is it enough? Bones and muscles are maintained through stress. They require a certain level of mechanical loading. In 1/6 gravity, that load is reduced or cut, but not eliminated. So what happens? Does the body interpret this reduced load as sufficient? Or does it interpret it as insufficient? And continue to break down these systems, albeit at a slower rate? That is the question we cannot yet answer. Animal studies give us some clues, but they are incomplete. Experiments in simulated partial gravity environments suggest that some aspects of the musculoskeletal structure are better preserved than in microgravity. Bones lose density more slowly. Muscles retain more of their mass. But the protection is not complete. It is not the same as under Earth's gravity, and the Apollo missions provide us with almost no data. The longest any human has spent on the lunar surface is less than 3 days. That is not long enough for most of these physiological changes to become measurable. It is not long enough to observe trends. So, Artemis will not just be a mission of exploration, it is a biology experiment. But that was only the beginning. The second epic moment. The problem of biological drift. This is not the failure of a single system. This is the accumulation of small physiological changes in multiple systems, simultaneously, under the same environmental stress. It is a system-wide departure from normal human biology. Bone density loss is expected to be slower in 1/6 gravity than in 0 gravity. But slower does not mean stopped. The mechanical loading is still reduced compared to Earth. This means the skeletal system is still receiving less stress than it expects. So, the body begins to remove material it deems unnecessary. The risk of fractures increases. Muscles rely on bones for leverage. Joints rely on them for alignment. As bone density decreases, the entire mechanical system of the body begins to change. This is an irreversible drift. Because in microgravity, astronauts can reset their physiology by returning to Earth. But on the Moon, that safety net does not exist. The astronauts remain in the same reduced gravity environment that is producing the change. So, the body continues to adapt. But without ever fully reversing those adaptations, this means that every week, the body drifts a little further from its biological baseline on Earth. And now comes the third epic moment, the reprogramming of the immune system. This is not a simple weakening. This is a restructuring of how immune responses are regulated. Consistent evidence from spaceflight research shows that the immune system behaves differently outside of Earth's surface environment. Certain populations of immune cells show altered levels of activity. Latent viruses in the body sometimes reactivate. Inflammatory markers change in ways that suggest the immune system is operating under a kind of chronic stress. How is this possible? Because multiple factors are at play simultaneously. Radiation exposure is much higher on the Moon than on the International Space Station. This can directly impact immune function. The psychological and physiological stress of isolation, confinement, and disrupted circadian rhythms all affect stress hormones. And those hormones suppress immune activity. And most importantly, the lunar dust introduces a completely new inflammatory load. Those sharp reactive particles irritate the respiratory system. So the body is under constant pressure from multiple directions at once. This raises the question of what happens when a real medical challenge is encountered. An infection? A physical injury? A dental emergency? There are no hospitals on the lunar surface, no specialists. Every medical intervention must be planned in advance and sent with the mission. This means the margin for biological error is extremely small. And now, the fourth, most unsettling epic moment. Psychological isolation. This is a layer that does not show up in blood tests or imaging scans. But it has emerged as one of the most significant limiting factors in every long-duration human isolation study. The psychological environment of the Moon. The human brain responds to patterns and sensory cues that have been reinforced by millions of years of evolution. But the Moon eliminates almost all of them at once. The sky is black, absolutely black. The absence of atmospheric scattering means sunlight does not diffuse. The sun hangs as a harsh, unfiltered white disk against a perfectly black background. The shadows are sharp and absolute. The stars are visible, even during what would be considered daytime. There is no weather, no clouds, no wind, no rain, no sound. There is absolute silence outside the habitat. There is no medium for sound to travel through. Inside the habitat, every sound is mechanical. Fans, pumps, electronics. The absence of natural soundscapes causes the brain to interpret this as a void. And on the far side of the moon, that blue and white disk of Earth, Ana, disappears entirely. There is no visual link to home. This is similar to the psychological effects observed in Antarctic winter over syndrome. Cognitive performance can decline. Emotional responses can be blunted or exaggerated. Insomnia and interpersonal tensions increase. But even in Antarctica, there is still a horizon, still air to breathe, still real-time communication. On the moon, none of that exists. This means the crew is not just isolated, but perceptually disconnected from almost all Earth-like reference points. And the psychological effects of this environment have never been tested over long durations. So when the picture is complete, what we face is not just an engineering challenge. It is a test of biological and psychological endurance. What will our bones and muscles do in 1/6 gravity? How will our immune system behave under the assault of multiple stresses? And how will our minds cope in an environment of absolute isolation and sensory deprivation? Apollo showed us that we could go to the moon. But Artemis is there to answer a much harder question. Can we stay on the moon? The answers to these questions will shape not only future missions, but humanity's potential to expand as a species into the solar system. But beyond these biological and psychological challenges, there is a larger strategic paradox that brings all these pieces together, a promise that the moon offers us, and at the same time, a trap hidden inside that promise. Because what awaits us at the south pole of the moon is not just a scientific discovery, but also white disk of Earth, Ana, disappears entirely. There is no visual link to home. This is similar to the psychological effects observed in Antarctic winter over syndrome. Cognitive performance can decline. Emotional responses can be blunted or exaggerated. Insomnia and interpersonal tensions increase. But even in Antarctica, there is still a horizon, still air to breathe, still real-time communication. On the moon, none of that exists. This means the crew is not just isolated, but perceptually disconnected from almost all Earth-like reference points. And the psychological effects of this environment have never been tested over long durations. So when the picture is complete, what we face is not just an engineering challenge. It is a test of biological and psychological endurance. What will our bones and muscles do in 1/6 gravity? How will our immune system behave under the assault of multiple stresses? And how will our minds cope in an environment of absolute isolation and sensory deprivation? Apollo showed us that we could go to the moon. But Artemis is there to answer a much harder question. Can we stay on the moon? The answers to these questions will shape not only future missions, but humanity's potential to expand as a species into the solar system. But beyond these biological and psychological challenges, there is a larger strategic paradox that brings all these pieces together, a promise that the moon offers us, and at the same time, a trap hidden inside that promise. Because what awaits us at the south pole of the moon is not just a scientific discovery, but also a strategic paradox. Because that water ice at the south pole of the moon is not an optional feature, it is the foundation upon which the entire long-term strategy rests. Without it, the vision of a continuous human presence on the moon collapses almost instantly. Water is life. Water is oxygen. But on the moon, water is also fuel. When you separate it into hydrogen and oxygen, you get the two primary components of rocket propellant. This single capability changes the entire architecture of space exploration. It allows missions to refuel off-world. It reduces the mass that must be launched from the surface of our planet. And in spaceflight, mass is everything. So, the ice on the moon is not a resource. It is the one resource that makes the entire concept viable. C'est sûr. But this is where the first epic moment begins. The strategic paradox. That ice we need is located in the most challenging terrain on the moon, in permanently shadowed regions. These are not just cold places, they are permanently dark places. Places where sunlight has not touched the surface for billions of years. This allows the ice to survive. But it also makes working in these regions extraordinarily difficult. Imagine working in a place with no natural light, ever. Every operation depends on artificial illumination, and the temperatures can drop to minus 250 degrees Celsius. That is colder than the surface of Pluto. At these temperatures, metals become brittle, lubricants freeze, electronics must be specially designed. And now, add in that seismic question from 2024, what our most valuable resource is located on what may be the most geologically unstable ground. How is this possible? How is it possible that the very thing we need most to survive is in the place that is hardest to reach and hardest to utilize? This is a pattern the moon presents to us over and over. The things you need are never in the easy places. They are hidden in extreme environments that test every assumption you bring with you. This shocked scientists and mission planners, because it proved that the mission was not just an engineering problem, but a geographical and geological puzzle. The resource and the risk were not separate problems. They were the same problem, and we had to solve them in the same place. And this brings us to the second epic moment. The trigger for the deep moonquakes. This shouldn't have been possible. We knew these quakes happened 700 to 1,200 kilometers below the surface. But what triggered them was a mystery. Until the Apollo data was re-examined with modern analytical techniques, and the answer was incredible. Earth. The tidal forces of the Earth were flexing the moon's interior so profoundly that it was releasing that stress as regular seismic events. This meant that our planet, from 400,000 kilometers away, was squeezing the heart of the moon. These quakes were happening with almost clockwork regularity, tied to the moon's orbital position. This proved that the moon was not just a passive satellite, but was in a constant, dynamic, gravitational dialogue with the Earth. This discovery was a startling reminder of how intricately interwoven planetary systems are. The moon was not just floating alone in space, it was being constantly needed by an invisible force, by our own planet. This showed us that to understand the moon's geology, we had to look not just at the moon, but at the Earth. It proved that the relationship between the two worlds was much deeper, much more physical than just orbital mechanics. And now, the third, most shocking epic moment, the source of the shallow moonquakes. This was one of the greatest mysteries of the Apollo era. We did not know what was triggering these more powerful, more dangerous quakes that reached up to 5 on the Richter scale. But data from recent orbital missions revealed a terrifying possibility: lobate scarps. These are small cliffs formed when one section of the moon's crust is pushed up over another, and they are the visible result of fault lines created as the moon globally cools and shrinks. These scarps were scattered all over the moon, and most importantly, they matched perfectly with the epicenters of the most powerful shallow moonquakes detected by the Apollo seismic network. This was the first direct evidence that the moon is still actively shrinking, and that this process is causing significant tremors on the surface. How could this be? How could a world assumed to be dead for billions of years still be contracting and breaking its crust? This showed that the moon's geological clock had not stopped. It was just ticking very slowly, and that slow process could have sudden and violent consequences for any human structure on the surface. This discovery created an earthquake in the scientific community because it proved that the danger of the moon came not just from the outside, from radiation and meteorites, but also from the inside. The moon harbored a threat within itself, and that threat was an ongoing geological process. These discoveries reveal a disturbing truth. One that the official celebrations and press releases quietly skirt around. The moon is not waiting for us. It is not a prize sitting on a shelf, patient and inert, ready to be claimed by anyone who shows up with the right hardware. It is not the grey, shark, silent geological museum we have imagined since grade school. It is something much more unsettling. And the farther those 4 astronauts travel from Earth, the closer they get to an environment constructed at every level, in every direction, with every available mechanism of physics, chemistry, and biology to destroy them. That is not a metaphor. That is a description of what the science is actually telling us. The dust is a biological hazard. The radiation is a persistent background threat that can turn into an acute emergency without warning. The temperature range exceeds what most materials on Earth experience in their entire lifetime. The ground beneath our feet is seismically active, and none of these dangers exist in isolation. They interact, they amplify each other, and they combine into a single survival problem that humanity has never had to solve for more than a few days. But now, it is time to pause amidst all these mechanical, biological, and geological challenges, and reflect. What do these discoveries, these brutal realities, mean for us? Is returning to the moon just an engineering achievement? Or does it raise a deeper, more philosophical question about the resilience and fragility of our species? Because behind every danger the moon shows us lies a greater truth, a truth about our relationship with the universe. And to understand that truth, because behind every danger the moon shows us lies a greater truth, a truth about our relationship with the universe. And to understand that truth, now is the time to pause and reflect. We are slowing down. We are moving away from the noise of shocking discoveries and epic moments to quietly contemplate what all this information means. This is not just about returning to the moon. This is about who we are as a species and what our place is in this vast, indifferent cosmos. And the first question we ask ourselves is perhaps the most fundamental one. How can this brutal environment, seemingly designed to destroy everything, and these incredibly fragile, biological beings who choose to enter it possibly coexist? The first contrast is between power and fragility. On one side, there is the moon, an entity that has been unchanged for billions of years that withstands micrometeorites traveling at 20 kilometers per second, that is indifferent to 300-degree temperature swings, and that is bathed in radiation. It is the definition of physical power: solid, durable, and almost eternal. On the other side, there is the human body, a system protected by a thin layer of skin, capable of operating within a narrow temperature range and in constant need of oxygen, water, and pressure. We can bleed from a paper cut, get sick from a virus, and succumb to the moon's standard radiation dose in a matter of years. We are the definition of biological fragility. When these two realities are placed side by side, the picture that emerges is almost tragicomic. It seems like madness that such a weak soul, such a delicate being, would even consider stepping into such a powerful and brutal world. Physically, we are more than a mismatch. We are an anomaly. An astronaut standing on the surface of the moon is no more durable than a soap bubble in a hurricane. Our biology does not belong in this environment, and the moon reminds us of this at every turn, as with its dust, its radiation, its temperature, its silence. But then comes the turn, because there is something missing from this equation. Yes, we are infinitely weaker than the moon physically, but we have something the moon does not have: the ability to understand. The moon may have existed for billions of years, but it is not aware that it exists. It does not feel its seismic activity, measure its radiation field, or know its own history. It simply is. We, on the other hand, despite all our fragility, can understand. We can record those seismic waves, decipher the nature of that radiation, and analyze the chemistry of that dust. The moon's power is a crude, unconscious physicality. Our power lies in our ability to understand that physics, to model it, and even to take measures against it. But the moon has the power to destroy us. But we have the power to understand it, and with that understanding, to develop strategies to survive. You are a part of this paradox too. You may have a lifespan of only 80 years in a 13.8 billion-year-old universe. But in that short time, you can learn about the billions of years of the universe's history. You may be a speck of dust in this vast cosmos, but that speck can think about the cosmos itself. Our strength is not in our muscles or our bones. It is in our minds. And that quality is a power the moon will never have. The second contrast is between permanence and transience. The moon is a monument to permanence. The craters on its surface preserve a billion-year history, almost undisturbed. The footprints left by Apollo, with no wind or rain, could remain there for millions of more years. The moon is like a place where time itself has slowed down. It is a geological archive, an unchanging record. We, on the other hand, are the embodiment of transience. Our lifespans are shorter than a blink of an eye compared to the age of the moon. Our bodies constantly change, age, and eventually turn to dust. Our memory is flawed. Our history is rewritten. We are in a constant state of flux. The moon is a frozen moment. There is a sad truth in this contrast. Whatever we do to the moon, whatever we build there, our presence will remain an anomaly on the moon's timescale. Our habitats will eventually degrade. Our equipment will fail. And we humans will leave those lands. The moon will remain. It was there before us, and it will be there long after us. Our presence will be just a brief whisper in its long, silent history. This is a reminder that humanity's place in the universe is tragically temporary. But there is a beauty in this transience as well, because the unchanging moon is also static. It is dead. We, on the other hand, thanks to our transience, are alive. We grow, we learn, we change, we create. The moon preserves history. But we make history. The moon is a monument. But we are the ones who live the moment. The Apollo missions themselves are a perfect example of this paradox. Those missions lasted only a few years in human history. But in that brief moment, we achieved one of our species' greatest accomplishments. We touched the surface of the moon. We learned about it. And we brought that knowledge home. Those moments were temporary, but the impact they created was permanent. They changed our science, our culture, and our view of ourselves forever. You are a part of this flow too. Every day, every hour, every moment of yours is fleeting. But within those moments lies the potential to live, to love, to create, and to find meaning. Something the moon has never experienced in its billions of years of existence. Perhaps our place in the universe is not to be permanent. Perhaps our place is to take these fleeting moments and infuse them with an infinite meaning. And this brings us to the third contrast: isolation and connection. The moon is the ultimate isolation. Silent, empty, and nearly 400,000 kilometers away from Earth. A person standing there is a small, lonely being, physically disconnected from the rest of their species. On the far side of the moon, even the Earth disappears from the sky. This is not just a physical separation, but a deep psychological disconnection. It is an overwhelming awareness of how vast the universe is, and how small we are, a sense of cosmic loneliness. The rest of the universe may be filled with galaxies billions of light years away, but in a practical sense, we are trapped on this small, pale, blue dot. To go to the moon is to experience this loneliness in its purest, most intense form. This is, on one hand, a frightening experience, where one confronts one's own insignificance, but right in the heart of that isolation, the strongest connection emerges. That lone astronaut on the moon, Mukt, is also one of the most connected individuals in human history. They are there through the collective effort of hundreds of thousands of engineers, scientists, and technicians spanning decades. Their mission is watched in real time by millions of people on Earth. And most importantly, the presence of that astronaut brings us together as a species. It creates a shared moment of humanity that transcends political, cultural, and geographical divisions. When we look at the moon and say, "We are there," that word "we" is the most inclusive version of humanity. You are a part of this connection too. As you read this text, you are sharing the thoughts of another person thousands of kilometers away. Now, as you watch this documentary, you are experiencing a shared moment of wonder and awe with millions of other people. We may be isolated in the universe, but we are connected to each other, and perhaps that is the deepest meaning of going to the moon. In that moment of greatest isolation, to discover our strongest connection. In that emptiness, to understand just how together we really are. These contrasts, power and fragility, permanence and transience, isolation and connection, show us that the moon is not just a piece of rock. It is a mirror in which we see ourselves. It shows us our fragility, our transience, and our loneliness. But it also reveals our power to understand, now our ability to create, and our bond with each other. the moon reminds us both of how small we are and how great we can be. But beyond these philosophical reflections, there is a more practical, more urgent question. Despite all these risks, all these challenges, and all these paradoxes, why are we going back? Is it just because we can? Or is what the moon offers us valuable enough to be worth all these dangers? Because the strategic logic behind the return to the moon involves much more than just a desire for exploration. And at the center of that logic, because the strategic logic behind the return to the moon involves much more than just a desire for exploration. And at its core lies another fundamental contrast: knowledge and the unknown. On one side, there is everything we have learned about the moon in the last 50 years. We know the chemistry of the dust, the dose of the radiation, the rhythm of the seismic activity, and the mechanics of the thermal cycles. We have landed instruments, collected samples, and mapped its surface in high resolution. Our knowledge has increased exponentially since the Apollo era. We know more about the moon than at any other time in history. This is a triumph of the human mind and the scientific method. But, on the other side, standing right in the center of that knowledge, is a vast unknown. We do not know what all of these factors, OXOR, when combined, will do to the human body and mind in the long term. We do not know the ultimate effect of 1/6 gravity on our bones. We do not know how our immune system will withstand the combined assault of radiation and dust. And we do not know how a group of people will psychologically hold together in that environment of absolute isolation and sensory deprivation. There is something tragic about this situation. No matter how much data we collect, no matter how many models we build, no matter how many simulations we run, we cannot answer this ultimate question on Earth, because this is not an equation that can simply be tested in a lab. This is an experience that must be lived. The moon itself is the only laboratory where the answer can be found. This is to accept that there is a limit to knowledge. No matter how smart we are, no matter how much we prepare, there will always be things we cannot control, cannot predict, and cannot fully understand. This, on one hand, carries a sadness of confronting one's own limits. But within this unknown also lies the most fundamental driving force of the human spirit, the desire to explore, because the things we do not know are also the things that push us forward. If we knew everything, there would be nowhere left to go. If every question were answered, there would be nothing left to ask. This is the essence of the Artemis program. It is a journey undertaken not just to confirm what we know, but to confront what we do not. It is humanity taking a step to the edge of the unknown. It is accepting that where the greatest risks lie, so too do the greatest discoveries. You live this balance in your own life. Every day, you act on what you know and trust. But there is also an uncertainty that comes from not knowing what the future will bring. And within that uncertainty lies the opportunity to grow, to learn, and to experience new things. Artemis is the grandest scale version of this personal journey. It is our species stepping out of our comfort zone and saying, "I don't know, but I want to find out." And this brings us to one final contrast: silence and echo. The moon itself is the ultimate silence. The airless vacuum does not allow sound to propagate. Its billion-year history has passed without a noise. Craters formed in silence. Mountains rose in silence. The existence of the moon is a massive, inaudible event. But opposite that silence is the echo created by humanity. From that first announcement of Apollo 11's landing, Houston, Tranquility Base here, the Eagle has landed, to Neil Armstrong's immortal line. One small step for a man. Our touch on the moon was defined by sound, by words, and by communication. We brought our own voice to that silent world. This, on one hand, shows how noisy, how intrusive our nature is. We are a species that feels the need to shout our existence into the silence of the universe. But there is a deeper meaning within that echo. Those sounds were not just technical communications or historical announcements. They were the expression of a species' shared imagination, curiosity, and hope. They echoed in the hearts of billions of people on Earth. Those sounds brought us together. They gave us a belief that we could achieve the seemingly impossible, and that echo continues to this day. When we talk about the Artemis program, when we plan new missions, and when we dream of returning to the moon, we are keeping that first echo alive. You are a part of this echo too. When you read a book about the moon, watch a documentary, or look up at the night sky and wonder, what is there? You are adding your own voice to that collective sound. The silence of the moon may represent the indifference of the universe. But the echo we create represents our search for meaning, our desire to connect, and our ability to find hope even in the darkest, most silent places. At the end of this entire journey, we find ourselves in a surprising place. We have been to the moon 6 times. We have walked on it. We have brought back 382 kilograms of rock and soil. But after a 50-year hiatus, we are realizing that much of what we thought we knew about the moon was incomplete or wrong. We learned that the dust is not just dust, but a biological hazard. We learned that the radiation is not just an occasional risk, but a constant and intense threat. We learned that the ground is not stable, but that it moves and rings, and we are still not sure if it is possible for the human body to live on the moon for a long time. When we face this information, 2 different emotions can arise within us. On one hand, a kind of fear and humility, a sense of being diminished by the understanding of how brutal the universe is, and how fragile we are. But on the other hand, a kind of awe and excitement, an inspiration that comes from the fact that despite all these challenges, we still want to go, still want to try, and still want to face that unknown. Both feelings are valid, because both are true. The moon is both frightening and inspiring, both dangerous and alluring. We are now approaching the end of our journey. We have peeled back the layers of the moon's hostility one by one, from dust to radiation, from seismic activity to psychological isolation. We have examined all the mechanisms that seem designed to destroy us. But we have also seen what these challenges reveal in the human spirit: our power to understand, our ability to create, our desire to connect, and that unwavering curiosity for the unknown. This was not just a story about the moon. This was a story about us. But now, with all this information, we return to that initial moment of celebration, the moment those 4 astronauts were going farther than anyone in human history. But now, we look at that moment with different eyes. We no longer see just progress and victory. We now see the risks, the dangers, and the unknowns. And this does not make that moment less heroic. On the contrary, it makes it far more meaningful. Because true heroism is not when there is no danger. It is when you know exactly what the danger is, and you step forward anyway. And now, we face one final question. After all this, what does the moon represent for us? Is it just the next target, or is it a mirror? And what we see in that mirror, on this journey, we discovered just how complex even a single world can be. But ask, what if I told you? This isn't the only reality that exists. Every decision you make may be creating a new universe, infinite versions of you, living infinite different lives. On our next journey, we will open the door to parallel universes and meet the other yous. Are you ready?